In this section, we're going to go over something called random variables. And to begin, I want to go over a couple definitions. So here, a random variable is a numerical outcome of a probability experiment. And just notation-wise, a random variable is denoted by an uppercase letter. And the most common one is the capital X. And there's two types of random variables. There is discrete and continuous. So a discrete random variable are just a random variable whose possible values can be listed, and a continuous random variables are just random variables that can take any values within some sort of interval. And if you recall, we already discussed about discrete and continuous values, so it's kind of like the same idea. So I want to do a couple examples. So here we want to choose whether or not these random variables are discrete and which are continuous. So the number that comes up on a roll of die. So you can see that this value here is discrete. And the reason why is that the possible values are a finite set of numbers. So here, or in other words, the values of these outcomes can be listed. So the possible value are 1, 2, 3, 4, 5, and 6. So if you imagine rolling a die, you're either going to get one of these values here. All right, so let's talk about the height of a randomly chosen college student. And when we think about height, there's not like with heights, the values of it could be within some sort of interval. So here, this random variable is continuous. Continuous. Because a person's height is not restricted to any list of values. In other words, that the height of a person could be within some sort of interval. How about the number of siblings a randomly chosen person has? So a person could have no siblings, 1, 2, 3. So recall that these values can be listed. So this random variable is discrete. Because it's kind of impossible to have like 2.3 brothers or sisters. How about the amount of electricity used to light a randomly chosen classroom? So the amount of electricity, there's no finite number. It's like within some sort of interval. So this gives you an idea that this random variable is continuous. So this is continuous. Cool. So in this chapter, we're mainly going to focus on just discrete random variables, and that makes the problem a little bit more easier. Okay, next I want to talk about something called a probability distribution, and we're going to see this a lot throughout this chapter. So a probability distribution for a discrete random variable specifies the probability for each possible value of that random variable. So for example, let's say that a fair coin is tossed twice, and let x be the number of heads that comes up. You want to find the probability distribution of x. So here, the number of heads that comes up, this is going to be our random variable, x. So here I just made a little chart and I just listed all of the possible outcome that could happen. So you could have heads, head, tails, tails, head, tails, tails. But we want to know the number of heads in each outcome. So here, on the first outcome here, how many head comes up? And there's 2. So we write 2 here, and now in a second, we see there's only one head that comes up. So you put 1. Here, again, we see 1. And here we have 0. There's no heads in this outcome. So let me just write down what I just did here. So here, for each outcome, we count the number of heads, which is the value of the random variable x. Cool. Now that we have the information, we can kind of construct a probability distribution. So what it's going to look like is that it's going to be like a little chart. So here we have your random variable x and the probability of x. So remember, x is just the number of heads that comes up. So here we want to ask ourselves, what is the probability of getting 0 head on an outcome? So if you look here, this happens 1 out of 4 because in total there's 4 outcomes, and there's only one possible way that we have 0 head, and this could be 0.25. Here we'll write 0 here as our random variable. The probability of getting 0 head is 0.25. Next, we want to know about what's the probability of getting 1 head in our experiment. So we can actually compute that. So the probability of getting 1 head is just, well, notice that there's only two possibility where that could happen out of these 4 outcomes. So this will be 2 over 4 or 0.50. So here in our probability distribution, we're going to write 0.50 below the 1. And finally, we want to know what's the probability of getting 2 heads in our probability experiment. So we write 2 here, and we want to know P of 2, or the probability of getting 2 heads in an outcome. So if you look at a little chart, that happens only 1 time out of the possible 4. So this will be 1 over 4, or 0.25. So here we write 0.25. And congratulations, this is a probability distribution for a discrete random variables. And we're going to see a lot of these, and we're going to ask a lot of questions about these. These probability distributions follow the same properties and law of regular probabilities. So if you recall, probabilities can't go over 1 because you can't be like 120% sure of something, and it can't be less than 1. So some of the properties of probability distribution. So here the probability distribution has a probability assigned to each distinct value, and that's what we see here. So each value here, like 0 has a following probabilities, 1 has a following probability, and 2 has a following probability. And another thing you want to note is that the sum of all of these probabilities has to be equal to 1. So let's determine some of the following tables here, or the following probability distributions, and see if they're valid. So if you see the first one, do you see anything wrong with this? Well, if you take the sum, if you add these up, it's actually going to be 1.18. Can this ever happen? And the answer is no. So that means this whole probability distribution is not a valid one. it's because when you take the sum of all these probabilities, it doesn't equal to 1. So let me write that down. No, because the sum is not 1. How about this one? Do you see anything wrong with this? Well, off the bat, you kind of see like we have a negative value here. So can a probability be a negative value? And the answer is no. It has to be between 0 and 1. So here, this whole probability distribution is not valid. So no, cannot have negative probabilities. Okay, last one. How about this one? Do we see anything wrong with this? Well, notice that each probability there's no negative numbers. And if you take the sum of this, it does equal to 1. So you say yes, this is a valid, or this is valid. This is a valid probability distribution. So let's look at this example. So here, 4 patients have made appointments to have their blood pressure checked at a clinic. So we're going to let X here be the number of them who have blood pressure. Based on the data from the National Health and Examination Survey, we are actually given a probability distribution X, which is this. So we're actually given a probability distribution to work on. And we want to find, we're asked to find a couple probabilities here. So here we want to find the probability of 1. So here, the probability of 1, if we look at our table, if we look at 1, the probability of 1 is just 0.41. So this is just 0.41. So this is just asking like, what is the probability that one of these patients has high blood pressure? So here, if in our probability distribution, 1, which is going to be our random variable X value, is going to have a probability value of 0.41. So here, P of 1 is equal to 0.41. How about finding the probability of 2 or 3? So if you kind of remember from our previous section about probabilities, the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. So we're going to do the same idea here, but with 2 or 3. So here, to find the probability of 2 or 3, it's just going to be the probability of 2 plus the probability of 3 minus the probability of 2 and 3. However, the thing is that 2 and 3 are mutually exclusive, so this is automatically going to be 0. So we're really just going to compute the probability of 2 plus the probability of 3. And we could find these values from our table. So the probability of 2 is 0.27, and the probability of 3 is 0.08. So this will be 0.27 plus 0.08, which gives you 0.35. So this is the answer. How about the probability of more than 1? So we want to know, what does more than 1 mean? Well, this kind of means just 2, 3, and 4. Because we're not actually including 1. because it's talking about more than one. So it will be 2, 3, and 4. So we could use the addition rule here. So the probability of more than one is just the probability of 2 plus the probability of 3 plus the probability of 4. And we already know these values from our little table here. So probability of 2 is 0.27 plus 0.08 plus 0.02. So this is probability of 2, probability of 3, and probability of 4. So this will be 0.27 plus 0.08 plus 0.01. And if you add them all up, it should be 0.36. Now we want to find the probability of at least one. So at least one, this means 1, 2, 3, 4. Now we could do what we did earlier and just do the addition rule, where we find the probability of 1 plus the probability of 2 plus the probability of 3, But what if we were given a table that was like really long? So in this case, what I would do is use rule of complement. So here, I would use rule of complement. And the reason why is because it's going to be a lot easier. So what is the complement of at least one? Like, what is the opposite? Well, this is going to be the complement of at least one is less than 1. So here, the probability of at least 1 is just going to be 1 minus the probability of less than 1. But what's less than 1 here? If you look at a table, it's only going to be 0. That's the only value that's less than 1. So this could be 1 minus, oops, forgot the equal here. 1 minus p of 0, which is going to be 1 minus 0.23. And put this in the calculator, it should be 0.77. And if you were to do the probability of 1 plus the probability of 2, 3, 4, if you add this up, it's going to be exactly the same value. But here, notice that I only did a little bit amount of work. It's going to be a little bit easier. So that's what you got to keep in mind. When you have like a problem where they ask you to take the sum of a lot of numbers, that kind of gives you an idea to use rule of complement, because it makes life a lot easier. So there's a big connection between probability distribution and a population, and also relative frequency. So here, a probability distribution of a random variable tells us the frequency that we expect from each of the possible values of the random variables that turns up in the sample. And we already did a lot with frequency and relative frequency. So here, for example, let's say that an airport parking facility contains 1,000 parking spaces. And of these, 142 are covered long-term space that costs $2 per hour. And 378 are covered short-term space that costs $4.50 per hour. 423 are uncovered, cost $150, and 57 are uncovered short-term space that costs $4 per hour. So let X represent the hourly parking fee for the randomly sample space, we want to find the probability distribution x. So we want to construct a probability distribution. So here, I made a little chart just to make it a little bit easier. So 423 parking spots were $1.50, 142 parking spots were $2, and then etc. So I just put all the information in a little table here. So here, we want to know the probability for each random variable. So here, we know that there is 1,000 parking spaces. So the probability of choosing one of the parking spaces that are $1.50 per hour is just 423 out of 1,000, or 0.423. And again, we can kind of do the same thing for this one. The probability of having choosing a parking space that is $2 per hour is 142. This is 142 out of 1,000, which is 0.142. And if you notice, what am I making here? I'm making a relative frequency, and that's what it is. So here, this will be, I'll just fill out the box for you. This will be 0.057, and this will be 0.378. So now we want to construct a probability distribution table, or a probability distribution. So here, we have all the information. This will be a random variable x, and this will be p of x. This will be $1.50, $2, $4, and then $4.50. And we know the probability because we just wrote it down. And again, these probabilities and relative frequency, they're both related to each other. So you have been doing probability distribution. Here we're just organizing a little bit better. So this will be 0.423, 0.142, 0.057, and 0.378. And now we just constructed a probability distribution. And again, we could just like ask the same questions. Like, let's say I could ask you like the probability of like 150, or like having a parking spot that's either $1.50 per hour or $4.50 an hour. And you could compute this, kind of like what we did earlier. So this is the same idea. We can even construct histogram out of these probability distribution. And the way we could do it is just exactly the same way we would do when we construct histogram for relative frequency distribution, when we're dealing with qualitative data. So here, we're dealing with discrete variables. So I would write down for this, x values will be here. So this will be 0, 1, 2, 3, 4, 5. So the goal is like I'm going to construct a histogram with this relative distribution. The the y-axis will be 0.05, 0.10, 0.15, 0.20, 0.25, 0.30, and 0.35. So notice that I'm not jumping again, so they're all a increase of 0.05. And then for 0 is 0.03125, so it should be around here. And then 1 will be all the way to 0.1565. So somewhere around here. So remember, since we're dealing with histogram, the bars has to touch one another. And then for 2 will be 0.31. For 3, it will be the same thing. And 4 will be here. And 5 will be here. And notice that I could ask like questions about the shapes of this histogram. So you notice that this is about symmetric, because if I cut a knife in the middle, the left half and the right half looks very similar. So this is symmetric. And I would write down, label the X and Y axis and put a title, but since this is just for an example and I don't know what they represent, I can't really do that. But yeah, we could make histogram out of these probability distributions. We could even take the mean or the average of these discrete random variables. And to do this, so let's say to find the mean of a discrete random variable, we multiply each possible value by its probability and then add these products up. So here, mu sub big X, so this is just notation. So this just means this is just the mean of the discrete random variable. It's mu, the Greek letter mu, and then a big X on the bottom of this. So mu of X. So to calculate the mean of the discrete random variable, it's just going to be x1, the value x1, times the probability of x1, plus x2 times the probability of x2, plus x3 times the probability of x. You keep going until the very end, and that will be the mean of the discrete random variable. Another way to write this is the summation of x times the probability of x. And then we could also interpret what this means. So the mean of the discrete random variable is the value that is expected to occur per repetition on average, if the experiment is repeated a large number of times. So this is what it means. Another thing you want to note is that the mean of these random variable, another word for them is the expected value. And the notation for this is E of X. But you could just write it mu of X too. So let's look at an example. A computer monitor is composed of a very large number of points of lights called pixels. So for example, like iPhones have very small pixels. Monitors also have pixels. Anything that's a screen has some sort of pixels. They have hundreds, even thousands of pixels. So it is not uncommon for a few of these pixels to be defected. So let X here represents the number of defected pixels on a randomly chosen monitor. And we were given this probability distribution. We want to find, the goal here, we want to find the mean number of defected pixels. So if you look back into what it is, what do we have to do to compute the mean? This is going to be, I'm just going to call it mu of big X is equal to x1, which is 0. So I got this 0 from here, times the probability of 0, which here is 0.2. So let me just write this down. So it'll be plus 1 times the probability of 1, plus 2 times the probability of 2, plus 3 times the probability of 3. So I got this 1 from here, this 2 from here, and then from the 3 from here. And these are all their probabilities. So I'm multiplying them up. So here, it will be 0 times 0.2, because the probability of 0 is 0.2, plus 1 times 0.5, because the probability of 1 is 0.5, plus 2 times the probability of 2, which is 0.2 plus 3 times 0.1, because the probability of 3 is 0.1. So if you add these up, this should be 1.2. Okay, but let's say I want you to interpret what this means. So in words, we could say that we would expect that the mean number of defective pixels on the computer monitor to be 1.2 on average. So this is what I'm looking for. I'm looking for expect and on average. So that's what I'm trying to look for when I ask you to interpret the meaning of these, the mean of the discrete random variables. If we could compute the mean of these discrete random variables, we could actually compute the variance as well. So here, the variance and standard deviation of a discrete random variable. So the variance is going to look a little bit different. It's going to be the summation of x minus the mean of the discrete random variable squared times the probabilities. So all we're doing here is just we're multiplying it by their respective probabilities. So that's the only thing that kind of changes. Here, x is just the value of the random variable, p of x is just the probability of x, and then mu of x, which we just computed, is the mean. The standard deviation of x is just taking the square root of it. So if this is our variance, then our standard deviation is just the square root of whatever that value is. So here, the variance and standard deviation are a measure of spread. So the variance and standard deviation of a random variable measures the spread in the probability distribution of the random variables. And then again, we could interpret what our standard deviation is. So a standard deviation is often represented as a measure of risk. A larger standard deviation indicates that the value of x is further from the expected value. A small standard deviation indicates that the value are closer to the expected value. In other words, a larger standard deviation indicates a greater likelihood that a data value is different from the expected value. So that's the interpretation of standard deviation. So let's look at the same example, but we want to compute their variance and standard deviation. So here, this is the same probability distribution of the defective pixel that we were working on. So again, we want to make a chart to organize our idea a little bit better, or organize our math. So x is going to be 0, 1, 2, and 3. So this will be 0, 1, 2, 3. X minus mu of x. So remember, we just calculate the mean of our random variable x, and this was 1.2. So this will be 0. I got 0 from here, minus 1.2. And this is going to be negative 1.2. This will be 1 minus 1.2. And I got this 1 again from this value here. This will be negative 0.2. And you kind of go along with the pattern. So this will be 2 minus 1.2, 0.8, 3 minus 1.2, 1.8. And then we want to square whatever value that we got to get rid of the negative. So this will be negative 1.2 square, which is just 1.44, 0.04 square. Oh, sorry, no. Negative 0.2 square, which is equal to 0.04. 0.8 square is just 0.64, and 1.8 square is 3.24. So here's going to be something different. We need an extra column to put our respective probability. So here, P of 0 is 0.2. P of 1 is 0.5. P of 2 is 0.2, and P of 3 is 0.1. So now, if you look at our little formulas here, we're multiplying this value with our probability. So we want to do the same thing. So here, the values that we got here, we're going to multiply with our respective probability. So this will be 1.44 times 0.2, which is equal to 0.288. And then I got this 1.44 from here, and this is just its respective probability. Now this will be 0.04 times 0.5, which is 0.020. And again, I got this value here from here, and 0.5 from its respective probability. And you kind of do the same pattern. So then this will be 0.64 times 0.2, 0.128. This will be 3.24 times 0.1, which is 0.324. Awesome. So now we want to ask ourselves, are we done? Are we finished? And the answer is no. Of course not. We have to actually compute our variance and standard deviation. So we haven't done that yet. We have to do one last thing. So remember that this symbol here means take the sum of all the values. So that's what we're doing. We need to take the sum of all these. So take the sum. This will be, I want to take the sum of all this. So in other words, I want you to add 0.288, 0.20, 0.128, plus 0.324. And this will be 0.76. So we could say that our variance here, so this is our symbol of variance, sigma square of x. There you go, I forgot the x. Sigma square of x. So this x means like we're dealing with a discrete random variable. This will be equal to 0.76. Okay, so again, this is our variance. Then to compute our standard deviation, sigma of x, we're literally just taking the square root of sigma square of x, our variance. We're taking the square root of our variance. So this will be square root of 0.76. And then if you do that, it'll be 0.872 if you round to 3 decimal places. Okay, so this, again, standard deviation. Okay, and that's how you compute variance and standard deviation of discrete random variables.